Okay, hi everyone. Today we'll be discussing this paper, Evolving Reinforcement Learning Algorithms by folks from Google. So it is a meta RL or sort of auto RL paper. So what they do is that they haven't proposed an RL algorithm in this. Instead, they have proposed an algorithm which automatically learns an RL algorithm. The algorithm actually predicts an RL algorithm which will work the best. Right. So that is the meta RL sitting here. And what they say is that they represent RL algorithms as a computation graph. So they say that RL algorithms can be represented as a computation graph. And their algorithm searches over the space of that computational graph to find the best possible computation graph, which is in fact the best possible RL algorithm, which solves the task, which performs the best. And they say that their learned algorithms are domain agnostic and they can generalize well. So that is pretty cool. Also, so when you are searching over the computation graph, there are two possibilities. One, your algorithm can learn from scratch. So you can start with an entirely random computation graph, which corresponds to an entirely random algorithm, and then it can search. It can. So the way it works, they work is that they uh, use an evolutionary algorithm. So they represent a computation graph. Then they make certain changes to that computation graph. They mutate it randomly, and they then evaluate it, and whichever one is the best on that evaluation, it passes on to the next generation, and then they keep on repeating this, right? So one way to do this is that you can start from scratch. Your initial thing could be a random thing corresponding to a random algorithm, which doesn't probably make much sense. So when they do that, they are able to and when they run the algorithm, their algorithm is able to rediscover the famous TD learning algorithm. So that is pretty cool. Another thing is that you don't need to start from scratch. You can actually start from a existing RL algorithm, like say DQN. They're saying like, okay, we can start from DQN, we can bootstrap from it, and so they represent DQN as a computation graph, and then they make changes to that computation graph, and so effectively their algorithm finds a more enhanced or more evolved version of DQN, which performs better than DQN. And in fact, in their experiments, they show that okay, their algorithm discovers two new variants of DQN, which actually performs better than DQN. So it is a pretty cool paper. Yes, I mean it. Uh, Such kind of approaches have the potential to discover new algorithms which work well, which is currently being done by researchers, but they are in the process of automating them, and it is pretty cool. So yeah, let's dive deep into the paper. Okay, so let's discuss the motivation, like why did they do this? So what this says that currently, if designing new RL algorithms is a pretty hard task because there are so many components that it is very hard to figure out how to combine them and how to get things exactly right so that everything works out. And it takes a lot of manual effort from researchers, right? So what they say is that maybe we can automate this process. We can learn algorithms which do this stuff automatically for us, and this would ease the task of researchers, and also it might actually find better algorithms that the researchers could themselves design manually. So, but still, you will need a researcher who designs the algorithm which finds the new RL algorithms. But then our work will be shifted to designing the meta algorithm which finds the RL algorithms. So, I mean, there will still be a human at the top too who has to design the algorithm, but their work would be less tedious relatively than actually figuring out the RL algorithm. Now they formulate their problem as a meta-learning algorithm with two loops. So you have an outer loop which searches over the space of computational graphs to compute the objective function for the agent to minimize. So basically you have an outer loop which searches over the computation graph, searches over the various possible computation graph. And what that computation graph represents is the loss function. So when you are training an RL agent, it best a deep RL agent, it usually minimizes some sort of loss function, right? So what the outer loop searches for is the loss function. The outer loop searches for a computation graph which represents the best possible loss function, and the inner loop uh, trains an agent based on that loss function to minimize that loss function. So the goal of the inner loop is to minimize the loss function learned by the outer loop, and the goal of the outer loop is to actually maximize the return of the inner loop and basically figure out the best possible agent. So basically, you have this big outer loop, and what it does is that in this you test out various computation graphs, and each of this computation graph represents a loss function. So this is somehow it will represent a loss function. So this is sort of a loss function L1. Now in the inner loop, what you will do is that you will take this L1 and then you will train an agent using this, right? So this is your inner loop, and what will happen is that okay, so this is your sort of inner loop, and let's make the outer loop even bigger. So in the inner loop you will train an agent, and the task of this agent would be to minimize this loss function. So the agent minimizes this loss function, right? And once you do this, you will get a agent, and then you will evaluate this agent. You will evaluate this agent, and you will get some reward. And the task of the outer loop is to maximize this reward. So to the task of the outer loop is to figure out the best possible computation graph which leads to the best possible loss, on which when you train an agent in the inner loop, it leads to the best possible reward. So this is how the outer loop and inner loop work basically. And this figure shows the overview of the method. So basically you have this, so it is an evolutionary algorithm. So you have this population of different computation graph, and each computation graph represents a loss function. And basically that loss function sort of represents our algorithm. So if you say TD learning, then there is a TD loss which sort of represents the TD learning algorithm. So you can represent the algorithm using the loss function which it has to minimize. And then since it's an evolutionary algorithm, you have a mutator. So what the mutator does is that it randomly changes the computation graph. It changes the loss function somehow. So you get a mutated algorithm, and then you use a train environment to train an agent using that mutated algorithm, and then you evaluate uh, your algorithm. You basically evaluate how much reward you got, and then using that reward you figure out, okay, what algorithms should make to the next generation, because it is an evolutionary algorithm. So you basically start with some algorithms, you make some changes, you evaluate which one performed best, and you use those as the parents for the next generation, and this process repeats over and over until you terminate and you hopefully find a good algorithm. So this is the overview. And this is a problem setup. So they are just focusing on discrete action value based RL methods for right now. So they are working on a discrete action space. They are not covering continuous action space, and they are only focusing on value based methods right now. So this is a constraint they have put right now. You will see that there are a lot of constraints in the paper. Their search space is hugely constrained to make it tractable to actually search through the possible algorithms. Otherwise, it would be it will require a hell lot of compute to search over this piece of algorithms. But okay. So in this, they'll have a Q value function, so which will basically be a neural network of some sort, and the policy is obtained by using the Q value function. So a Q value function is basically q of s comma a, which given a state represents how good is it to take an action. And since the actions are discrete, to figure out the policy would be to take an argmax over a. So argmax of over a is your policy pi, because obviously you will take the action which is the highest possible value, and since it is a discrete action space, this argmax is actually easy to calculate. You can just figure out the q value at every possible action and take its argmax. If it was continuous, then things become weird, but we are not covering it here. Then they use a replay buffer. So basically the agent, while learning, saves the transitions it made in a replay buffer, and you, which consists of state, next state, action, and reward tuples, and you basically use the loss function to, so your goal is to basically update the policy. You have to update the policy such that you minimize the possible loss function on the transactions. So you have a replay buffer in which stores all the possible transitions, and what how you train your agent is that you take those transitions, you put them in a loss function, you get a loss value, and your aim is to update the policy such that that loss value is reduced over these particular transitions, and you use gradient descent for that. Other constraints are that training will occur for a fixed number of episodes, and in each episode the agent will get some return, and the evaluation metric for them is normalized average training return, which is represented by this. So normalized here means that it is normalized on the range of the rewards you get, R max and Rmin, and they assume that the R max and Rmin are known ahead of time. So basically they assume that for an environment you already know that what is the maximum reward or the minimum reward you can get from this. So they normalize the reward based on this, so that if you have an environment where the range of rewards is like 5,000, and you have another environment where the range of rewards is just 10, you need a way to compare them and to weigh them equally, so they have to normalize the rewards. Also, take notice that they have taken an average. So what will happen is that this will also account for sample efficiency, because this is a summation over the episode. So this is not just the final reward you get after you have trained the entire agent. So if your training curve, if your reward versus steps curve looks like this, a lot of times people just evaluate here, like what is the final reward I got after say 1 million steps. They're not doing that. They are averaging the reward over the entire learning process. So this accounts for sample efficiency as well. So sample efficiency basically means that how quickly your agent is able to learn. So an agent which is able to learn quickly would get a higher normalized average training return, because its curve would be something like this. And when you take the average, even though if they get the same, or even if this gets a higher return, I'm assuming this would be higher, and this is actually better because you need to take the sample efficiency into account as well. You can't train your agent forever. You want your agent to train early as well. So yeah, they used normalized average training return to account for sample efficiency, both for sample efficiency and also the range of the environment. I'm focusing on this much because evaluation in RL is a bit weird, and people evaluate in weird ways which actually don't make sense a lot of times. There was also a paper which won the, I think, the outstanding paper award at UNIPS or something. I'll link to that paper, which gave a set of metrics to how to actually evaluate algorithms. So just that evaluating RL algorithms is a thing that requires some research in itself. And here they show basically how the computation graphs are. So this is the computation graph for a DQN. and it is a computation graph which computes the loss function of this familiar loss function of dqn. So as you can see, it has input states, next states, then you have theta. Theta is basically the policy function, and I think they have theta and theta dash, so I assume these are the target and current networks. You have two networks in dqn, right? And I think NN is a neural network, and which maps states to a list of rewards. So this is basically the queue function which maps state to a reward for each action, I think. And they are taking the max, so which is the argmax, the discount, and stuff, and then they are basically taking the L2 distance. So this is showing how you can represent the DQN algorithm loss using a computation graph. And once you represent this as a computation graph, you can actually do mutations in this computation graph. You can say, okay, maybe this reward also goes here, or maybe this gamma also goes here, or maybe there shouldn't be L2 distance, maybe there should be an L1 distance. It can search over that space and automatically figure out a good loss function which leads to the highest reward. And here they state that the goal of the meta learner is to find the optimal loss function to optimize pi theta with the maximum normalized average training return over the set of training environments. So argmax, so this is the objective of the meta learner. Argmax over L, so it has to find the best L, and L is this computation graph which represents the loss function, which maximizes the eval L comma epsilon over all epsilon. Epsilon here represents environment, L is the loss function, eval is basically this normalized return. So you have to find the best possible loss function which leads to the highest normalized training returns over all the possible environments. So that is the objective of the meta learner. Okay, so now they talk about the search language, which is basically how they represent the computation graph. So the input nodes of the computation graph basically include elements from transitions like state, action, next state, reward, and also constants like the discount factor. You can see here that the inputs are state, action, discount, and rewards and stuff. All right. And the parameter nodes are neural network weights which can map between various data types. So the parameter nodes could be, for example, the weights of the Q value network, which map state to real numbers for each action. Basically, which maps Q of S comma A. This is a wonderful S. S to A with which takes in a state and it gives a reward for each action. And you can see these parameter nodes like here, this NN node. There are also operation nodes which compute outputs given inputs from parent nodes, which basically perform an operation. Now these operations could be different things. They could be applying the parameter nodes. So like passing the inputs to a neural network, or basic math operations like basic math operators from linear algebra, probability, statistics. Also, they set the last node in the graph to compute the output, and the output should be a scalar loss function. So they constrain that the last thing should be an operator which finally gives us a single scalar which the losses output. Also, they say that importantly, their inputs and outputs are timed among state, action, vector, float list, and probability. And this allows for programs to be applied to any domain while also restricting the space of programs with only valid typing. I mean, you can have some rules across, okay, this type, if this type is the input, then this type could be the output only. So that allows for some constraints to restrict the search space as well. And also, it also makes the thing more general in some sense. For the evolutionary search method, they use something called the regularized evolution. And the way, because it has been used for some supervised learning algorithms, and it can also be parallelized over computer nodes. And they definitely need parallelization because the task requires a lot of computation. So it works through tournament selection. So you have a population of P algorithms, and you improve the population through cycles. Each cycle picks a tournament of T less than P algorithms at random and selects the best algorithm in the tournament as a parent. A parent is mutated to a child algorithm, which gets added to the population while the oldest algorithm is in the population. So basically, what you have is you have a population, you have multiple different uh, samples in it. I mean, each sample here represents algorithm. Here each sample represents a computation. So this is actually a entire computation graph which is some sort of loss. And the evolution works in tournaments. So in each cycle you have a tournament which is a subset. You choose a subset of algorithms. You use each of these algorithms to train an agent. You evaluate those agents and you get a reward. And you pick the best agent, the loss which led to the best agent as a parent. So suppose this is the loss which led to the best agent, then this would be the parent of the next generation. And what happens is that you take this, you mutate it somehow. So you mutate it into a what to say a child algorithm, and this child algorithm is added into this population, and the oldest algorithm is removed. So say if this was the oldest algorithm in this population, it gets removed. So this way your population is increasingly evolved into children's or mutations of the algorithms which performed well, and the hope is when you repeat this enough, then you will get a very good algorithm as the byproduct. For the mutation, they say that they only focus on a single type of mutation, which first chooses which node in the graph to mutate. So it chooses, okay, which of the nodes should I mutate? Should I mutate this? Should I mutate that? And then it replaces it with a random operation node with inputs drawn uniformly from all possible inputs. So what it does is it first chooses, okay, out of random, it chooses which node should I mutate. Say it chooses this node. Then it replaces this node with a random operation node. There could be any operation node here. And then after that, it uniformly randomly connects all possible inputs to this operation node. So this is how they mutate their computation graph. Now what this says that, okay, there are competent comparatively large number of graph configurations. So if they have to search over the entire space, it is not feasible for them to search the entire space. So instead of that, they add some constraints to the, or they add not some constraints, they add some checks to prune uh, useless computational graphs to make for a more efficient search. So one of them is functional equivalence check. So what they say is that if I have one computation graph, this is one computation graph, this is another computation graph. If both of these are functionally equivalent, I mean basically they represent the same function somehow, I will not use this one. I will why use this one. I mean they do use it, but they use it in a way they use it. They don't really use it, sort of use it. They cover here. Okay, so they add it to the population, but use the saved score of the older program. So they will use the score from this program. But they do add this to the competition, but they don't evaluate on it. They just use the score from the previous, from the functionally equal program. The reason they add this is because maybe in the future this will lead to something interesting. Because they are just functionally equivalent, they're not exactly equivalent. So maybe a mutation would lead to some interesting result here and might not lead to an interesting result here. They also use early hurdles. So basically, they have this cart pull environment, which is pretty easy to solve. And they say that if particular uh, if a particular algorithm is not able to solve the easy environment, then we will not further mutate it and we will remove it from the population. Then there are also program checks, which are basically some heuristics to remove algorithms which don't make any sense. So because the output should be a loss function, they say that the output types should be a float. So if the output type is not a float, then they will remove that algorithm. And they, since we have to train using gradient descent, they also check if the program is differentiable with respect to the policy parameters. And they do this by checking if a path exists from the policy to the output. If a path exists and it is a computation graph, then you can use backpropagation to calculate the gradients. Then they say how they learn from scratch versus how they bootstrap. When they're learning from scratch, they initialize the algorithm randomly. And this is done by sampling each operation node sequentially in the DAG. DAG is basically the computation graph. DAG is a directed acyclic graph, which basically is a computation graph. You can think of it as is the computation graph. And basically, when they are learning from scratch, they sample everything sequentially, uniformly, randomly, and they get a random computation graph. But when they bootstrap, they take the loss function of dqn to bootstrap. So the first 7 nodes represent the standard dqn loss in their computation graph, which they start with bootstrapping, while the other remaining nodes are initialized randomly. And the interesting thing is that these 7 nodes are not frozen. It is not as if these 7 nodes can't be mutated. If the algorithm wants, it can entirely change these 7 nodes. It is just a template to start from a bootstrap now. Now let's look at the experiments. So first of all, they only search over 20 nodes. So their computation graph consists of a maximum of 20 nodes. Even then, they required 72 hours across 300 CPUs to find everything, which is an insane amount of compute. Not really feasible for a student researcher like me, I guess. As for the training environments, so their idea was we should have training environments which are both computationally expensive to execute, but which also covers a diverse set of situations. So they went with 4 classic control tasks: cart pull, acrobat, mountain carnival, ladder, and also 12 multitask gridworld style environments from minigrid. This is cart pull, and probably this is minigrid, this is lunar landing, and this is also some game Atari games. For the hurdle environment, they used cartpole. So the hurdle environment is the environment which is used for pruning algorithms. Cartpole is they say that cartpole is a pretty easy environment, and if an algorithm is not able to solve it well enough, we should probably not waste effort on mutating it. And also, all of the neural networks are MLPs. They're not using CNNs or any complex architecture. They're simply using MLPs, I think, which also means I guess they are directly accessing the states and they're not working on images most probably. So okay, at the end of training, they saw that roughly 70% of the algorithms are functionally equivalent to previously validated programs. So 70% of them are 70% of the algorithms find algorithms which were anyway which it had found before itself. So this means there's a lot of redundancy. It is both good, it is both bad. It shows that their experiments are repeatable, that their approach is able to find those solutions and again, but it also means that they are doing a lot of redundant computation, which could be optimized. And also, easy hurdles cut around 40% of the proposed duplicate programs. So, yeah, I think this is a great heuristic which they used, which allowed for pruning a lot of algorithms which wouldn't have led to any good algorithms. So, here they show the number of algorithms evaluated versus the evaluation performance. The difference between them is that the blue curve only was trained on one environment, the orange on 2 environments, the green on four environments. So as you can see, as we increase the number of environments, we can increase the performance, I guess. And the red line here shows the bootstrapped one. So the red line actually bootstraps from DQN and it performs the best, and also its sample efficiency is pretty high. As you can see, it learns pretty quickly. So bootstrapping also helps in sample efficiency. And on the right, we see the distribution of the number of algorithms and how well they perform. So a lot of algorithms, most of the algorithms end up performing poorly, but a lot of them also get very high results. As you can see, these get a very high results, and a lot of them perform poorly as well. Most likely, these guys would get pruned, and this would go to the next generation, sort of. So, yeah. An interesting thing they showed here is that while they were learning from scratch, the algorithms were able to learn the TD loss, this TD loss by itself. So this was from scratch, and from scratch only it figured out to tweak the computation graph in such a way that it leads to the TD loss. But the interesting thing was that the single environment thing, the one which was only trained on single environment, learned this function, which did not had the gamma term here, the discount function here, while the one learned on two environments was able to add this gamma as well. So they say that increasing the range of difficulty of the training experiments can allow to learn algorithms which can generalize better. Because when you increase the number of training experiments, the number of training environments, you got the actual TD loss with the gamma in it, which is the actual correct thing to do to discount losses. Whereas in a single environment, you got a version which was a bit poorer and which didn't have the gamma inside it. Now let's look at the bootstrap experiments. So what happens is that when they run the bootstrap experiments, their algorithm learns two variants of Q-learning, which they named DQN clipped and DQN regression. So first coming on DQN clipped, the discovered loss function sort of looks like this. Here, gamma is this, delta is this. Delta is basically delta square is what the Q standard DQN loss is, and as you can see, what this is that what happens is that in this thing, if you solve this, then if the Q value is too high, if the Q value is greater than the delta square, then the loss would act upon minimizing the Q value, because this term would become active and then you will have this term would become active and then you will have to then the algorithm would minimize the Q value. So what it does is that if it is sort of acting as a regularizer on the Q value, if the Q value becomes too large, it will focus on decreasing the Q values. And this is a good thing because there are algorithms called conservative Q learning. So what happens is that in reinforcement learning, the problem is that the Q values are the network is overly optimistic and it overestimates the Q values, and that leads to weird performances. So a lot of effort is done to reduce the Q values. You have double DQN, you have DDQN and stuff. So it is interesting that their method itself figured it out that it needs, not only does it need to uh, minimize delta, which is the DQN loss, which is the sort of temporal difference loss, it also needs to focus on minimizing the Q values, so the network automatically learns that. Also, the second algorithm, DQ regression, is a more simpler version of this, which the first one has sort of this weird switching behavior where it switches between different loss terms. The second one is more simpler and it has the standard DQ loss, but it also has this regularizer, which is always present and which regularizes the Q values to prevent them from going too high. And fairly enough, they tested their algorithms on variety of environments, and they saw that uh, the RL algorithm that was bootstrapped from DQN by their algorithm basically outperformed other existing RL algorithms like DQN, DDQN, PP, and stuff. So yeah, their algorithm automatically finding an RL algorithm that is pretty good, and it is far better than the algorithm it bootstrapped from. So it is sort of doing the work of researchers itself. Here they analyze the reward curves, the Q values, not the reward curves, the Q values of the learned algorithms, and they saw a pattern. So DQ and overlay. So here the purple line represents what the actual Q values should be. So assume we have access to the oracle and we calculate the Q values. So the purple line is where the Q values should actually be. What happens is that DQN overly estimates the Q values. As you can see, this rises here. DDQN underestimates. I mean, DDQN does not overestimates, and it is able to. It underestimates the Q value and it converges to the optimum Q value. Their proposed DQN clip is sort of similar to DDQN, but it has this. It underestimates even more aggressively, while DQN regression totally under is sort of pessimistic initially and then it stabilizes. So dequin regression is very pessimistic in the beginning and then it sort of even in the end it underestimates the q values, and this is that they say that underestimating is actually good because they point out to these various research works which show that overestimation is bad and restricting overestimation improves performance. So even if this underestimates the q value, it is a feature and not a bug sort of thing. And here they analyze the dequin clipped. So what they say, so the dequin clipped has these two max terms, and based on the switching, this leads to four cases. And they say that there are two special cases. Case 2 corresponds to minimizing the q values, whereas case 3 corresponds to the normal delta square loss. So what they observe is that they analyze the proportions where each of the cases is active during training, and they see that case 3 is usually most active in the beginning. Sorry, case 3 is the case which is mostly active, but initially case 2 is active. So case 2 regularizes the q value. So what they observe is that initially it is case 2 which is active. So the network learns to minimize the q values initially, but after that the network switches to case 3 which is just the normal dequin loss. So the network learns that initially there is a good chance that the Q values are being overestimated. So it switches to case 2, which minimizes the Q values. And afterwards, it automatically switches to the normal decline loss. So this is sort of mind blowing that the network automatically learns these things, that when to switch between different algorithms, when to add the regularizer, when to remove the regularizer. So this was pretty awesome. So yeah, that was really it for the paper. They tell some limitations here. So they say that basically their main limitation that they themselves acknowledge is that their approach is very restricted in the type of algorithms it searches for. So they just focus on discrete actions, value-based algorithms that are sort of close to DQN. So it is a very restrictive space. And the reason for that is probably because it will become computationally expensive to search over an even larger space. Uh, so I think interesting future work in this would be like how to figure out how to expand the space efficiently. So one critic, not a criticism, but sort of a comment is that most they themselves say that most of their algorithms are redundant and a lot of the algorithms discover the same thing. So a feature work, an interesting feature work would be to have some sort of weighted sampling which predicts okay how much, because they're mutating everything randomly, there might be some way to guide that process to make it not random, to have maybe another network which predicts the mutations, or basically some sort of way to guide the process more efficiently and not really relying on just brute force random evolutionary approaches. So that might lead to more optimized search, and that might allow them to expand their search space even more to more general RL algorithms like this as actor critic or policy graded. But yeah, overall it was a pretty interesting work. I mean, uh, they are proposing an algorithm which basically does the work of RL researchers by themselves. So it was pretty amazing, and the fact that it was able to learn AD loss by itself or enhance DQN was pretty awesome. Like I was hoping that okay, maybe I can just use this algorithm in my Algorithm project and it will improve its performance or it will find a new algorithm by itself. So yeah, it was pretty amazing. Yeah. So that's all for this video and thanks for watching.